All right, section 5.5 is about calorimetry. So calorimetry is a process where we measure the enthalpy change, delta H, of a chemical reaction. So you guys have heard of calories before. Maybe you've seen like on food, it says how many calories the food contains. That's how much chemical energy is contained in that food, and your body is able to release that energy and turn it into other forms like heat and like kinetic energy for your body to use. And so in order to get the values on the packages of food, calorimetry would be done, where chemists would release the energy from the food and they'd measure how much energy is released. And we're going to learn in this section about how that's done, not just for food, but for other chemicals as well. The energy in food is usually measured in calories. That's just kind of the standard that we use. In chemistry, we typically measure things in joules or kilojoules. You can convert from kilojoules to joules pretty easily. 1 calorie is equal to 4.18 joules. So it's a pretty easy conversion. If you see things in calories, you can convert it to joules and vice versa. But most of what we do is all going to be measured in joules or kilojoules. So a calorimeter is an insulated container filled with water, and you can measure the amount of heat transferred by the reaction because it's equal to the heat released or absorbed by the water. So in the class, in the lab, we're going to see pretty simple calorimeters. Sometimes an insulated container is just like a styrofoam coffee cup. It actually works surprisingly well to get accurate data using a simple calorimeter like that. In other chemistry labs, they obviously use things that are a little bit more high tech, but essentially the things that they always have is they have an insulated container, and then they're typically filled with water because we are good at measuring how much energy water absorbs or releases. Okay. The basic principle in calorimetry is that since you're in an insulated container, right, so we're in an insulated container, it's a closed system, and we know that energy can't be created or destroyed, it can just be transferred. So if we have a reaction and it's surrounded by water, we know that any heat that the reaction gives off is going to be picked up by the water, and any heat given off by the water is going to be picked up by the reaction. It can't go anywhere else because it's in an insulated container, a closed system. And so it can only go between these two things. We know how to figure out Q of the water, how much heat's released or absorbed by the water, and we can use that to figure it out for the reaction. So we need to understand specific heat in order to be able to do calorimetry. The specific heat of a substance is how much energy it takes to change the temperature of 1 gram of that substance by 1 degree Celsius. So if you have just 1 gram of water, which is a very small amount of water, and you want to increase its temperature by just 1 degree Celsius, maybe from 20 to 21 degrees Celsius, how much energy does that take? Well, it takes the specific heat of water, which is 4.184 joules of energy to change 1 gram of water by 1 degree Celsius. So a joule is a pretty small amount of energy. If you have more water, so if you have 2 grams of water, it's going to take twice as much heat. Or if you want to increase its temperature by 2 degrees Celsius, it's going to take twice as much heat. So the equation that you're going to use is probably the most important equation in the chapter. Q, the amount of energy, is equal to the change in temperature times the mass times the specific heat. The specific heat of water is 4.184 joules per gram degree Celsius. Other materials have other specific heats. Water has a fairly high specific heat. It takes quite a bit of energy in order to get water to change temperature. If you think about like a piece of metal and a glass of water left out in the sun, and think about they're both the same size, have the same mass, and they're both left out in the sun for the same amount of time, the water will get a little bit warmer, the metal will get a lot warmer. So it's easy to change the temperature of a piece of metal. Metals typically have low specific heats, but water tends to maintain its temperature pretty well. It takes a lot more energy to increase or decrease the temperature of water because it has such a high specific heat. So here's kind of a simple calculation to help us understand specific heat. How much heat is required to heat 450 grams of water from 34 degrees Celsius to 67 degrees Celsius. So the first thing we want to do is calculate our temperature change. So our temperature change here is just the difference between where the temperature started and where it ended. So delta T is going to be the final temperature, 67 degrees Celsius, minus the ending temperature, 34 degrees Celsius. So you have a temperature change of 33 degrees Celsius is our temperature change. It went up by 33. Your delta T can be negative or positive. In this case, it's positive because the temperature went up. All right, so now we use this equation. So Q, the amount of heat, that's what we're trying to find. It says how much heat is equal to the temperature change. So positive 33 degrees Celsius times the mass, right? The more water you have, the more heat it's going to take in order to change its temperature. 450 grams of water. And then the specific heat of water, 4.18 joules per gram degree Celsius. All right. If you have other substances, you still use this same equation. Like say it was a piece of aluminum, you'd still use this same equation, but you'd have a different specific heat. Every different substance has a different specific heat. For water, we're going to see this one a lot, so you'll probably remember this number. For other substances, it's always going to be given to you, or you'll have information that'll allow you to find it. So we multiply those together, and you get 62,132 joules. Joules are really small amounts of energy, like I said before, so you get a big number. A lot of times, just to make it easier to deal with, we change it to kilojoules. So this would be equivalent to 62.1 kilojoules. All right, so now we get into a calorimetry problem. So now we're going to use that information about water in order to figure out for a different reaction how much energy is released or absorbed. Okay, so it says a 0.5 gram sample of lactic acid. So we have 0.5 grams of HC3H5O3. So that's our sample. Is burned in a calorimeter. So an insulated container, you're going to have a combustion reaction taking place, and this is going to give off heat. And that heat is going to be absorbed by the water in the calorimeter. So here's my water. And in this calorimeter, I have 1,000 grams of water. And the temperature of the water goes from 25.4 degrees Celsius to 26.9 degrees Celsius. All right, so we're in an insulated container. It's some kind of calorimeter. So we have an insulated container. We have our reaction down here. And the reaction is a combustion reaction. It's giving off heat. So as these chemical bonds are broken and new ones are formed, heat was released. And that heat goes into the water, which is your surroundings. And we know how much water we had, and we know what the temperature change of the water was. So to do this calculation, we're going to first find Q of the water. How much heat was released or absorbed, in this case absorbed, by the water. And to do that, we're going to use the equation from the last slide, which is Q is equal to delta T times mass times specific heat. Okay, so the temperature change of my water, 25.4 up to 26.9, so it's 1.5 degrees Celsius temperature change. The mass of the water, it's 1,000 grams. And the specific heat of water, 4.18 joules per gram degrees Celsius. All right, so we multiply those together, and I believe you get 6,270 joules. Okay, we'll make that into kilojoules just to make it a little easier to work with. So 6.27 kilojoules. Okay, now the whole concept in calorimetry is that Q of the water, however much heat the water released or absorbed, is equal to Q of the reaction, but with the opposite sign. Okay, so since energy is not created or destroyed, any energy that the water released is absorbed by the reaction, or any energy that the reaction released is absorbed by the water. So we're going to take this same number for the reaction, but make it with the opposite sign, so make it negative. So here Q of the reaction is equal to negative 6.27 kilojoules. So that's how much energy was released during this reaction. Okay, we're not done yet because we just burned some kind of arbitrary amount of lactic acid. And if we want to compare our results with other lab groups or with the standards, we don't want it for 0.5 grams necessarily, but we want it for 1 gram or 1 mole. So to do that, if we got this many kilojoules for 0.5 grams, we can divide kilojoules by grams to get kilojoules per gram. And then we want to change it to kilojoules per mole as kind of the standard way of reporting your enthalpy changes. So we want to change grams to moles. So we'll put grams here, moles here. We'll add up the molar mass of the lactic acid, which comes out to be 90 grams per mole. And so now grams can cancel out, and you'll be left with kilojoules per mole. And this comes out to be negative 1128 kilojoules per mole. All right, so it's important that you guys have the negative sign here, showing that this is an exothermic reaction. Anytime the water gets hotter, you know that the reaction must have released heat, so you know it's going to be a negative sign for the reaction. Okay, and so this is your enthalpy change in kilojoules per mole of this exothermic reaction. Let's look at one more calculation similar to that. This one is ammonium nitrate dissolving in 100 grams of water in a calorimeter, and the temperature is going to, in this case, drop. And we want to calculate delta H, the enthalpy change, how much heat is released or absorbed for this process. All right, so here our reaction is 3.88 grams of ammonium nitrate, NH4NO3, and it's dissolving in 100 grams of water. And the temperature is going from 23 degrees Celsius to 18.4 degrees Celsius. So this is a little bit different than the last problem because the temperature change went down. You still do all the calculations the same, but in this case, the water is losing heat, and the reaction, or these chemicals right here in your system, are absorbing that heat. So heat's being transferred the opposite way. So we know right away this is going to be an endothermic reaction. Endothermic reaction because heat is going into this and out of the surroundings, which is the water. We'll do this the same way. So we'll first calculate Q of the water. And so to do that, change in temperature times mass times specific heat of the water. This one's a little bit different in another way, and that is that the ammonium nitrate is actually mixed in with the water. So the ammonium nitrate, as it dissolves in this water, is actually becoming part of the solution. So when I calculate Q of the water, it's going to be really Q of the solution, this water and ammonium nitrate mixture. So the temperature change here is from 23 down to 18.4. So that's going to be a temperature change of negative 4.6. So negative 4.6 is my temperature change. Okay, important that you put the negative sign. And then the mass is going to be not just 100 grams of water, but it's going to be the 100 grams of water plus the 3.88 grams of ammonium nitrate. So your total mass, 103.88 grams. Not going to be a huge difference if you just used 100 grams, but the proper way to do one of these problems where the chemicals put into the solution is to include the mass of the salt or whatever is being dissolved in with the mass of the water and get the total mass of the solution. It's also kind of standard to assume that this solution still has the same specific heat of water. It still releases and absorbs energy at the same rate that water does, so still 4.18 joules per gram degrees Celsius. Okay, so we have our temperature change of the solution, our mass of the solution and our specific heat of the solution. We'll multiply those together and you get 1,997 joules. Okay. So now that we've gotten that, now we know that Q of the water is equal to Q of the reaction, but with the opposite sign. So in this case, the water, oops, I forgot my negative sign up here, sorry. Okay, so since we had a negative temperature change, we have a negative energy because it's being released by the water. Therefore, the reaction is going to have the opposite sign. So here, Q of the reaction is going to be positive 1,997 joules, or 1.997 kilojoules. Okay, so you're always changing the sign between what the water did and what the reaction is doing. The reason this water got colder is because the reaction took heat, took energy away from it. All right, just like before, we used kind of an arbitrary amount of ammonium nitrate, and so we want to figure it out per gram, so divide by how many grams of ammonium nitrate we used. And then we want to find it out per mole. So we'll change it from grams to moles. We'll add up the molar mass, and it's 80 grams of NH4 NO3 for every 1 mole. Okay, so grams are canceling out, and then we're going to be left with kilojoules per mole. And when you do that on your calculator, you're going to get that delta H is equal to positive 41.2 kilojoules per mole. All right, so you know that this one is endothermic because delta H is positive, which is the opposite of what our last example was. But the rest of the process is basically the same.